I'm Rachel.
And I'm Patrick.
We're going to be talking about photolithography. Um, okay, so the world we live in today is full of innovation. From Tesla's self-driving cars to portable drones, technology is definitely advancing. However, it was not always like this. Imagine loading Google, but the letters in Google loading every 10 minutes. Frustrating, right? Your grandparents or even your parents have probably experienced this loading of Google, like Google's first edition, and from then, the history of processors or transistors of major companies like Google or Yahoo have evolved into the advanced nano-sized ones today. My group and most of society waits for the newest things to come out, such as the iPhone 8 or surgery-performing robots. But these things are here today because of science. And in particular, photolithography is one of the fundamental processes that creates these innovations.
So photolithography involves many steps that ultimately transfers a pattern onto a surface. So just a little brief summary of what we did. So our first step is to place a mask on the surface of a board and place a coating of photoresist. So this will allow the pattern of the mask to be seen when exposed to UV light and a solution. So the UV lights will ultimately weaken the chemical bond and will allow exposed parts to be etched off so you can get your final pattern. And after this is placed under UV lights, a coating of developing solution is placed so that these exposed parts will be etched off and you can get the pattern that was intended for. And so after the etching, the remaining polymer is removed with a stripper solution, so it completes the process and you actually get the pattern. So the picture we're going to describe is the process of actually drawing like an actual like art and like placed in a gallery. So the first painting in the top left is just a blank picture without the rose or the flower, which represents just the surface with the photoresist solution on it. And then the one to the right of that is with the actual pattern and the board to support the actual thing to support the board. And then the picture in the middle left, it's adding more detail just to prove how intricate these designs are at a closer range and how detailed these patterns will get. So, and then in the middle right, it actually shows two different things. First of all, it shows how after using like UV lights and adding the solutions and etching everything off, you get the intended pattern. So as you can see, like the support is gone and it's only the actual material that's needed. And then also it shows what happens when it's factored down or scaled down 5 times, which just proves its functionality as seen in the bottom left picture of how the multiple uses of this picture, which is in a locket or above a fireplace. And finally, it's placed in an art gallery to kind of bring a broad topic of a clean room, which is basically in this situation with an art gallery, the art should not get dirty because dust or in this case, any mud or dirt can damage the art. Similarly, in our experiment, cleaning rooms are intended to keep dust out, and because dust will damage the actual polymer or the surface. And that's about it for the drawing.
So I'll talk to you guys about pretty much how photolithography affects the world. So like in the modern days, pretty much everything, smaller is better. And for example, back then computers, how they were really big and they could only store a few gigabytes. Now, due to photolithography, these chips have been or technology has been able to shrink them down, and they can contain hundreds of gigabytes, which is a lot more than before. And another example would be in cars and airbags. So back then again, the cars would usually have airbag systems that were positions all throughout the car in order to ensure the safety of the passengers, and this was really inefficient because like again size, and now pretty much they've technology has shrunken down this airbag feature into mini microchips. And for example, if you get in a car accident, this chip could sense if there's enough force, the airbags will be deployed, which is again smaller and more efficient. And this is also a more cost-efficient method too. So yeah. Questions?
Okay, I'll start. All right, so you explained a bunch of aspects of this, and you explained how the experiment worked. So this drawing only captures some aspects of that experiment. So can you please discuss, when I said think about your words, I didn't say don't talk about the limits of these drawings, because they all have limits. So could you talk about what aspects of the experiment, particularly like the really key aspects, are not captured, and how you might include them in a drawing like this?
So one thing that we particularly noticed was we did not see a transition with the UV light and the idea of coating, like coating after the UV light's coating with a developing solution, which a quick solution to that would be just adding a light over the actual portrait while working on the portrait to kind of demonstrate how there is actually a light there in like the middle two drawings.
What about the concept of pattern transfer?
Hold on.
Convene, 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 convene. Mumble, 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 mumble. Talk, 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 talk. The idea of pattern transfer. How might you add that in? So what specifically would represent the mask in this drawing?
Well, it could be in the first photo in the top left. You see, it's kind of hard to tell, but that little shaded portion on the actual portrait before the pattern is there, it's like right. It's in between. It's hard to tell, but if you looked at the actual drawing, it's there. It's like a little like like shading sort of. So that's what we thought it would be.
Okay, so there's actually a pattern on the first one.
Yeah, it's just kind of, it's hard to tell, but if it's on the actual paper, there's a little pattern.
Just the base coat. Which one do we have three of? Okay, so I get one more chance to get all the concepts across. Okay, then you only have to have part of the concepts there. Okay, so let's do some other questions.
So it's pretty much in the lens where first you would start off like with a bigger design, and then you would use like you would shine a light through it, and you would use the lens to bend the light, which will then project the image, and like pretty much it would go like this direction, like the light, and then it'll just pretty much just shrink the image down, and then you just go through the same process as this, and you'll get your product pretty much. Yeah. Yeah, exactly.
Okay, so can you get as small as they really are just using a magnifying glass? And if not, why not?
That's a good question.
Yeah.
All right, well, start first. As the first one's yes or no, so you got 50% odds. Can you is a magnifying glass enough to get down to current Intel chips?
Oh.
Probably not.
Okay, no.
No.
Any idea why not? What's the limit of what you can do with light?
Isn't it like half the size of the wavelength?
Yeah, it's some function of the wavelength, and it's bigger than what you're currently getting. So they do focus, and then they also do all sorts of other crazy, weird, stupid things, like they have patterns that are overlapping patterns, and only in the little region where they overlap do things get fully exposed. So light enough in a magnifying glass is not enough to get as small as they are. You have to play a lot of other games that I don't even know all the details of. But just be aware that just a magnifying glass is not sufficient to get to what is current chip size. They're in the world of really crazy games with light to do that lithography.